Hello, everybody, and welcome to another episode of PyTorch Community Voices. My name is Suraj, and I'm your host for today. I am also a developer advocate and developer at Facebook AI. Um, you might have noticed that today's episode is slightly earlier than our previous weeks. This we did this deliberately so that we can be more accommodating of all time zones. If this is still an unreasonable hour for you, I'm sorry you couldn't join us today. But feel free to leave your views and questions and any comments that you'd like to share with us in the comments below. And I'll coordinate with Shagun, who's our guest today, to have them answered and responded to. So without further ado, I'd like to call on Shagun. Hey, Shagun, good to see you.
Hey, good to see you as well.
Shagun, we are very glad to have you here today. You'll be talking about multitask learning and multitask reinforcement learning, and
Yes,
that's a pretty cool topic, and I believe it's close to the cutting edge as well. Um,
yes.
and I'm excited to learn more about this, as I'm sure all of our viewers are. But before we jump into that, Shagun, can you tell us a little about yourself?
Yes, so I'm Shagun. I'm a research engineer with Facebook AI, part of the Facebook AI research org. I've been with Facebook for about 2 years now, and before that, I was a grad student at Miller, working with Yoshua and Jian, and before that, I was at Adobe Research, and then undergrad before that. So that's pretty much all my industrial journey.
Awesome. I'm again. Thanks for taking the time out today. And so, as the viewers can see, Shagun is going to be speaking about multitask reinforcement learning. The way our episodes are usually formatted is Shagun will be presenting his slides for about 15 to 20 minutes, during which all comments are open. So please feel free to type in your questions or any views that you'd like to share with Shagun in the chat. And once we have gone through the presentation, we'll be opening up the floor to Q&A, and that's going to be a more interactive sort of session. So feel free to dial in your questions while the presentation is going on. We'll definitely be getting to them after. Shagun, before we get into the presentation, would you mind giving us a few sentences about multitask learning? Just the paradigm of multitask learning.
Yes. So the idea is, if we forget about reinforcement learning and if we forget about machine learning and neural networks and everything for a minute, what does multitasking mean? It basically means that I am doing multiple things at the same time. And why should we care about it? Well, we should care about it because first of all, when I'm doing multiple things at the same time, right? There's a possibility that what I learned by doing one task can help me to improve my efficiency, my performance, my speed of learning on the other task. And this is pretty much how we humans operate, right? Let's say I want to read a physics book written in French. So the first thing I'll do is probably learn French, and then I read the book. And now I want to read a book on chemistry, again written in French. So what happens now? Do I go back, relearn French, and then read the book? No, I already have some skills, some knowledge that I can transfer from one task to another, from the task of reading a book on physics to a task of reading a book in chemistry, and I leverage that. I reuse my knowledge, I reuse my skills, and this is how we operate in the real world. Now, this is how we benefit from multitask learning. And now the next question is, can our machine learning models, can our reinforcement learning agents can also benefit from this? So if they are being trained on multiple tasks, does the fact that they have already been trained on some tasks provide some meaningful priors for them to transfer and learn new tasks? So that's where the whole, the importance and value of multitask learning comes in. Basically, learn a few tasks so that you can learn other things faster.
Right. Very similar to how humans also learn
Yes.
in general. I guess multitask models try to understand the latent properties that are evident in similar tasks,
Yes.
and use that latent understanding to inform how they predict, or how they whatever they're predicting on the various tasks.
it can be done both ways. There's this bottom-up way where, I have to do 5 tasks and I figure out what's common between them. And then there's this top-down view where I'm already telling you, look, these are 5 books. These 5 books have these things in common. So, if you want, you can just first understand what this common part is and then read the 5 books. But yes, in both the cases, the common theme is that there's some structure, there's some knowledge which is shared across the tasks, and we leverage that to improve our learning or our speed of training on the other task.
Very interesting. Thanks for that context, Shagun. Now, if you don't mind, we are very excited to see what you have to present.
Yes, let's share my screen. Okay, so can you see my screen now?
Yeah, perfect.
Great.
I'm going to take myself backstage. The floor is all yours.
Thank you. So in this particular talk, we would talk about environments and baselines for multitask reinforcement learning. So basically, we'll be talking about this new library, or actually 2 libraries that we worked on recently. And I want to call out my collaborators who helped me throughout the process to create these libraries. So there's Amy, there's Ludovic, Pierre, Alexander, and Olivier. All of these guys are from FAIR. So before we talk about multitask reinforcement learning, let's just do a quick primer on reinforcement learning to make sure everyone in the audience has the same background. So what's happening in reinforcement learning? We have got an agent. An agent is a model or a network that we are trying to train. And this agent is interacting with an environment. An environment is basically anything and everything outside of the agent. So there's an agent. The agent is interacting with the environment. And this interaction goes in the following way. The agent observes the environment. So agent observes some state of the environment, which is commonly denoted as S. And then the agent, it predicts an action, or it takes an action in the environment. So the agent observes the state and it takes an action. And along with the state, the agent also has access to some sort of reward from the environment, which tells the agent whether the action that it took was a good action or not, or whether it was the best action or not. So this is how basically the interaction is happening. And the goal for the agent here is learn a mapping between states to actions, which is commonly called as a policy. So learn a policy such that it can maximize the returns or the expected reward it would get from the environment. So this is the single task reinforcement learning, or the standard reinforcement learning view, right? So you have an environment, you have an agent, and there's this interaction. Where does multitask learning come in, or how does the multitask learning view of the same problem looks like? So this is one way the multitask reinforcement learning could look like. So there's this one agent which is interacting with multiple environments. So it sees an observation from environment 1 and it predicts an action, and it gets a new observation and a reward, and it does the same thing with all the environments. Now, it could be doing this thing with all the environments at the same time, or it could be doing it more of a sequential way where, for example, in one step, it interacts with a subset of environments, and in the next step, it interacts with a different subset of environments. So these, this flexibility is there. You do not have to interact with all the environments at once. You can choose which environments you're interacting with and so on. And you could very well say that, look, this is not different environments. Like you can consider all of them as one single environment. So you can say that instead of thinking about these 7 environments as different environments, there's one big meta environment, and the agent is just interacting with that one big meta environment, and it's getting observations and reward from all of them. So this is the other way of looking at the multitask reinforcement learning, where you could say there's actually just one environment, and we are getting some state which encapsulates all the information, and the reward that we are getting is corresponding to multiple tasks. And both these views are equally valid. In some cases, assuming or starting one view would probably make the problem more tractable. But in essence, these views are more or less similar. And this probably also explains how we generally think about multitask learning, right? Like we could say that we want to train an agent which can do 10 things in the same environment. So that an agent which can learn to pick objects and clean the room and place the objects at the right place in the same room. And that's the view where you have one environment and multiple reward signals. Or you could say, oh no, I want to learn a policy or an agent which can do different tasks in different environments. So the agent should be able to read a book and cook food and clean room, and then you can think of these as different environments. So the key takeaway here is you can do multitask reinforcement learning with multiple environments, or you can think of them as one single environment with sort of different reward signals. So with this sort of quick primer about multitask reinforcement learning and reinforcement learning, let's come to the to the more, the focus of this presentation, which is environments and baselines. And the question is, why should we build environments and baselines for multitask RL? Well, the first thing is it's an important problem. Multitask reinforcement learning is an important problem. And as Suraj was asking at the start, why do we care about it? Because humans leverage multitask learning, and they leverage multitask learning to become better learners. So if humans can do that, maybe this is a useful inductive bias for our algorithms as well. So that is one view. So that's one reason for building these baselines and environments. And the second is we want to make it easy for people to get started in this field. We want to lower the barrier, and we want to have these libraries which are easy to use for people to get started in this. So that's the second motivation for building these toolkits. So that brings us to the code base. So what exactly, or how exactly is this code base structured? So there are two main pieces for a multitask RL code base. There would be the environment, or the multitask RL environments, and then there would be multitask RL algorithms. And we have two separate libraries for each of them. So for the multitask environments, we have this library called as MTN, which is basically a collection of environments, and I'll talk more about it. And then we have this other library called as MTRL, which is basically a collection of multitask RL algorithms and baselines. So let's start with MTN, which is the collection of environments. You can go to this URL right now and get the library and access it. So MTN, what's the goal here? What are we trying to build with MTN? There are two goals. We want to standardize the multitask RL environments. And what does standardization mean? We'll talk about it in a minute. But we want to standardize the multitask RL environments. And we want to provide better benchmarks for multitask reinforcement learning. So for people to evaluate their algorithms, there should be better benchmarks. Let's start with the standardization part. So people who work in reinforcement learning, they are very likely to be familiar with this thing called as OpenAI Gym. OpenAI Gym is a very, very popular interface, probably the most popular interface for reinforcement learning environments. And OpenAI Gym is not just an interface, but a collection of environments. But let's see how that interface looks like. So when you're using OpenAI Gym, you would do something like an import gym. So you import the library, then you make an environment. You can reset the environment and get the first observation. Then you tell your algorithm, okay, we are going to do n number of steps. For every observation, you can get an action out, and then you can execute that action in the environment. So this API where you make an environment via gym.make, you get the observation by doing, or you reset the environment by doing env.reset, and then you step through the environment by doing env.step. And in the end, you can close the environment with this in.close. So this is what I mean by the interface. OpenAI Gym has provided this interface which has made it easier for people to get started, because now people can reuse algorithms from each other, or reuse algorithms coming out of different repositories and so on, without worrying about how the environment looks, as long as they follow this interface. And this is what I mean by standardization. So having this fixed interface is the standardization, and it basically means that if I want to try my algorithm on your environment, I don't need to know anything about it. As long as it follows the interface, I can just swap out your agent with my agent and still train it and see how it performs. So this is super useful. But the problem is, OpenAI Gym is by default it's designed for single task environments or single task RL problems. It is not designed for multitask RL. So what it means in practice is you cannot control the task state. And what does task state mean? So let's say I start an environment and I say, there's this environment and the agent has to learn on it. In the single task view of the problem, all that I get from the environment is basically the environment's observation. But in the multitask view, there's also the state of the task, the task that needs to be done. And Gym does not provide control for the task state. The environment observation is sort of first-class citizen with OpenAI Gym, but the task information is not. So this is one place where we think that standardization is useful, and it doesn't mean that you cannot use the Gym API to do it. You can, in fact, you can do it in multiple ways, and that's precisely the problem. Since you can do it in multiple ways, the standardization goes away, and since the standardization goes away, it's difficult for me to take your environment or any other person's environment and just swap out the policy with my policy and hope it would work, because now we are relying on implementation details which are not standardized across the environments. So this is where we come into the picture, and we hope that we'll be able to standardize our multitask RL environments through this library. So what do we do? Well, we extend the OpenAI Gym API to add support for multiple tasks. And there are two main guiding principles that we have. We want to make as few changes as possible to the Gym interface, because Gym interface is super cool. It's super useful. People are familiar with it. It works. So we don't want to break the interface just for the sake of it. So we want to make minimal changes to the interface. And the second thing that we want to ensure with the MTN API is it should be easy to take existing environments, whether they are single task or multitask, and it should be easy to port them into this MTN library. So that's the second goal that we have, or the second guiding principle we have. So how does the standardization part look? So Jim is going to return an unstructured observation, which is just an environment observation. MTN would return a structured observation, which is basically a dictionary with two keys, the environment observation and the task observation. So the environment observation is what Jim would generally return, and task observation is anything which is specific to the task that the agent has to solve. And other than that, there's really no change. So the same kind of loop can be used with MTN as well. So Cardboard V1 here could very well be an MTN environment. And all of this interface would remain exactly the same, with the difference that environment is now the observation that you get from the environment. It's now a dictionary, and it's not just a unstructured object. So as long as your policy handles that part, you can swap out policies very easily. So basically, there are minimal changes to the environment interface. And looking at it, it pretty much feels there are no differences. The only change happens in the observation side. The second difference that happens, which is sort of hidden away from the user, or at least hidden away from the interface of using the API, is that task information becomes a first-class citizen. So internally, you'll have a task information that you can control. And what it means is you can set separate seeds for the task information. You can change the task information on the fly. When you are resetting the environment, you can say that I want to reset the environment, but I want to set the task to task number 5 instead of task number 1. So you get that kind of control without changing the user-facing API. And then the second part is that the second guiding principle that we had was we want to make it easy to port the environment. And for that, we provide multiple wrappers. So you can start with a single task environment, wrap it into an MTN wrapper, and get a multitask version out. You can bring a sort of collection of environments, and you can wrap it into and get a multitask environment out. So we provide multiple wrappers for that. As of now, these are the environments that are supported. So there's Acrobat, DMC, MetaWorld, MoveFastRL. This is a congestion control environment. So some of the standard environments are already supported. And the future steps from our perspective are adding new environments, releasing new benchmarks, and extending the library. So what we have right now, it's still not perfect, still not complete, because, for example, we do not cover the case where the different tasks could have different observation spaces, or we do not cover the cases where different tasks could have different action spaces. So there's space for making contribution there by extending the library for handling these cases. As I was mentioning earlier, the library is already released. So if you want to check it out, it's available at Facebook Research/MTN. If you just want to install it and play with it, it's available at PyPI. So you can just do a pip install MTN. So that covers the first part, which is about the environments, which is just the environments and the interface. Now we are going to talk about the algorithm side, or the agent side, or the policy side, which is MTRL. MTRL has this high-level philosophy that we want to provide two basic components, and people should be able to combine these components. So the first component that we provide is a base policy. Think of a base policy as a single task RL algorithm, or a single task RL agent. And then the second component is this sort of collection of components, actually, that would take any base policy or any single task policy and sort of tweak it to work on multitask setup. So there are base policies, which are basically single task policies, and then there are components which you can sort of enable, which would extend this base policy for the multitask setup. So what does base policy mean? Well, base policy is a collection of components like actor, critic, encoder, decoder, transition model, and so on. So when you're creating your base policy, you can enable or disable certain components. So for example, you can make a base policy just with the actor, critic, and an encoder, and that would be a vanilla SAC policy. Or you could use all these components, and that would look more like a deep MDP style single task policy. So there are these components that you can enable or disable, and you can instantiate these different base policies. The more interesting part is the multitask RL components. So what are the different multitask RL components that we support? So let's think about the different multitask RL problems, right? One multitask RL problem could be where the agent has to perform a task, and the agent is given some sort of task ID. So the agent is told that it is performing task 1, and how does it perform the task? So you may want to use some sort of task encoder, which takes the task ID as an input, generates a task representation, and concatenates it with, let's say, the observation from the environment and feeds it as an input to the policy. Or you could have a setup where you know that you are operating in multitask setup, but you do not know which environment you are in. And then you have to infer the environment, or you have to infer the task that you are performing. So you might have some sort of context, and you may use a context encoder for inferring that. Another flavor of multitask RL would be where we use gradient manipulation algorithms. So think of the problem as you're trying to solve a two-task problem, and the standard issue is when you take gradient updates for one task, that can interfere with the gradient updates for the second task. So in this case, you don't really care about task IDs or so on. You are just taking vanilla gradient updates, but these updates are interfering. So what can you do? You can project away the gradients such that there is no interference between them, and that falls into this broad category of gradient manipulation algorithms. So we have two gradient manipulation algorithms, PC-grad and grad norm. A third sort of setup where you may want to use multitask RL is you have, let's say, a shared policy trunk, but you want to have different action heads. So you want to have different heads in the network to predict the actions for different tasks. So in that case, you can use these task-specific components. A fourth case would be where you say that I'm going to train one policy for every task. So if there are n tasks, I would train n different policies. And then I would distill these policies into a centralized policy. And an example of that is distill, which is also supported. So these are four different flavors of multitask RL for which we provide support in terms of components. So you can take whatever component fits the best for your use case, enable it, and see how well it performs. So let's take an example. So let's say I want to use the actor, critic, encoder, decoder as the basic components for making my policy, and then for making the single task policy into a multitask policy, I want to use multiple heads. Multiple heads basically mean you have the shared representation, and for each task you'll be making an independent prediction. So how does that work? How would that look like if you were to do it using the library? So I'm assuming here that we are doing it for the meta world environment. The environment comes from the MT-in. MTRL is just a collection of algorithms and baselines. So let's see. So this is the command that would do it for you. So let's break down this command into pieces and see what each part is doing. So the first line is standard Python path, Python 3. So it's like standard Python stuff, nothing to do with the library. We go to the next step where we are saying that we want to train it on meta world, and specifically we want to use meta world MT10. So MT10 is a suite of environments or a suite of tasks in meta world which has 10 different tasks. We say that we want to use a state SAC agent because a stateful SAC agent has all these four components. And then we specify the multitask component that we want to use. So should the agent be using multitask policy? Yes, it should be using it because that's the component we want to use. And that's it. So you can take it, you can run it, and your agent would start training. Now, the core value proposition here is that these multitask RL components are really plug and play. So you can enable one of these, you can disable rest, or you can enable multiple ones, let the other ones disable, and so on. So let's say instead of doing a multi-headed policy, I want to use single head, but I want to use a mixture of encoders. So everything remains the same as it was last time. The only thing that changes is instead of a multi-headed policy, I want to use a mixture of encoders. So how would the command change? Well, this is how it would change. And just to contrast it with what really has changed is, instead of saying that I want to use multiple heads, I'm saying that the agent should be using, the encoder type that the agent is using should be a mixture of experts. That's it. And just to contrast this with what we had earlier, the only thing that we changed is the multitask RL component. So even in the command line, the only part that changes is the multitask RL component, and everything else remains the same. And then the question is, if this is really plug and play, why do I have to choose one of these? Can I do both of them? Yes, you can. So now I'm saying that I want to use the mixture of encoders as well as the multi-headed policy. And so I'm just enabling both of these things at the same time. So these components are really plug and play. You choose what you want to use, and you enable it via the command line, and that's it. So the library would compose the agent for you, and you'll be able to train it and see the performance. And now let's say I want to use mixture of encoders, but I want to specify that I should be using 4 encoders. Yes, that's doable. So you specify that you want to use mixture of encoders, and then you specify that the number of experts or the encoders that should be used is equal to 4. So again, it's very much composable and doable. And there are multiple such examples. I'm obviously not going through the entire exhaustive list, but this gives you a sense of how the library is designed. You should be able to choose the multitask RL components you want to enable them, and then just run it. And let's say if I wanted to do the same thing, but this time I want to do it on MT50, which is another suite of tasks from MetaWorld. So the setup remains the same. I just specify the environment to be MT50, and everything else remains the same. So it creates the environment, it figures out the shapes and everything, and it starts training the policy. The key takeaway here is, again, the part that you need to change is the only part that you need to change even on the command line, and everything else would be composed on the fly. So if you want to play with MTRL, it is also available on GitHub. So just go there and clone it and play with it, and let us know how that looks like. What are the future steps for MTRL? Yes, so basically we want to add more base policies, and we want to add more components. In terms of base policies, we are basically supporting SAC and policies built on top of SAC, but we also want to add support for PPO, Impala, and other things. And then in terms of other components that we want to add things like context-aware dynamics models. We want to add hypernetworks. A hypernetwork is the high-level idea with the hypernetwork is you provide it a context or a task encoding, and it would generate the weights of the network that can solve the task for a given setup. So we want to add support for hypernetworks. We also want to add support for trajectory-based context encoders. We have already made some good progress on the last 3 components, that is context-aware dynamics model, hypernets, and the trajectory-based context encoders. And we should be able to push out a change in a few weeks from now. But there's still a lot of scope for making, adding more base policies and components. And then there's this other side of scaling the setup and making it more easier to use. So we want to have more memory efficient replay buffers. We have made some progress on this side as well. Should have an update soon. We want to scale the policy components, have examples of more complex training pipelines, and provide pre-trained weights and models so that people do not really even have to train these things. They can just use it and use it as a starting point for training a policy on something else. That's it. So that's all I had about multitask RL, the environment, as well as the library or the collection of baselines and the algorithms. Yeah, thank you very much.
Shagun, that was so crisp. Thank you for that very clear presentation. You distilled a fairly complex topic in a few slides, and I think you did a great job of that.
Thank you.
I would say the audience also agrees. For those of us who are joining now, we just heard Shagun talk about the libraries that his team has built, MTRL and MTNV. These are libraries that basically help you do research and build your own multitask reinforcement learning applications. It houses a number of algorithms and environments that are optimized for multitask learning, reinforcement learning. Make sure you check out the projects. The GitHub links are in the video description on YouTube, and it's also on the YouTube chat. I will also be sharing the URL later at the end of the stream for posterity so that you can easily take a look. So Shagun, we are going to open up the floor to questions from the audience. We already have quite a few of them. I'm just going to run through them right now. Nico on Facebook asks, what's the difference between multitask learning and meta learning? Thank you, Nico, for your question.
Thank you, Nico, for the question. At a high level, the difference could be seen as what do we want to evaluate the policy on or evaluate the agent on. So let's say I'm training the agent on 50 environments and I'm going to evaluate the agent on these 50 environments, then it's probably more of a multitask learning problem. Whereas if I am training the agent on on a collection of environments, and then I want to see how quickly the agent can adapt to a unseen environment, which I have not sort of trained it on, then that's more of a meta learning problem. There are components that you can sort of share between them, and there are insights and ideas that you can share between them, but that's like one way of making a clear distinction between these.
Right. Thank you, Shagun. Tyrone asks, is multi-environment learning just like having an agent drive multiple types of cars?
Yes, that's a completely feasible, completely logical multitask problem. A more natural way of thinking about multi-environments in context of, for example, self-driving cars is you have trained the car to run on a concrete road, and that's awesome. But tomorrow you take out your car and it's raining, and your algorithm does not really know how to drive on a wet road. Is it a separate task? Are you going to consider the same task? You could very well say that driving on concrete road is one task, and driving on a wet road is a different task, and driving on a snowy road or a road covered by snow is a third task, and so on. So that's also a way of thinking about multitask learning or multiple environments in context of, for example, driving.
Thank you, Tyrone, for that question. Shagun, I wanted to ask you, is multitask learning and reinforcement learning a well-studied subject?
It is well studied. So there are three ways to look at it, right? One is the theoretical perspective, then the other is more of empirical perspective, and then the third perspective is it mature enough that we are starting to use it in real production use cases or real life use cases? From a theory perspective, yes, there's a lot of theoretical work on multitask learning, reinforcement learning, and so on. So there's strong theoretical backing to many of these works. From an empirical side, it is reasonably well studied. One sort of challenge is, and it goes back to the motivation of the libraries is different people would use different flavors of multitask learning, and then it becomes less obvious as to, hey, how do I compare with them, or where does my multitask algorithm fit in? So that sometimes leads to issues like not realizing that other people are working on very similar problems and sort of reinventing the solution. So sometimes it leads to problems like that. Sometimes it leads to problems like reproducibility. So people are not just able to reproduce each other's results. So in that sense, yes, it's well studied, but it has a lot of nuances and sort of pitfalls around it. And then the third perspective is yes, sorry.
I'm so sorry. Please go on.
Okay, and then the third perspective is the field sort of mature enough that we can start using it in real life applications. We are seeing more and more applications of it, but this is one place where you can. It's like it's like asking, is it good enough? I mean, it can always be better. So we are starting to see applications, but obviously that scope can increase a lot more, and it could be applied at a lot more places.
Yeah, I was just going to say that I believe the standardization that MTRL and MTN introduces would probably assuage some of these challenges that you mentioned.
Hopefully, yes.
I want to bring up Bhuvaneshwari's question. They wonder if you have some papers on multitask RL that you believe would be good reading in the space.
Yes, I'm happy to share some links. Do you want me to do it now? Should I send it to you and then you can put it along with the?
Yeah, maybe we can add links to the papers in the video description or in the YouTube comments as well. Bhuvaneshwari, please stay tuned for that. And thank you for bringing up this important question. And I was wondering if can you use MTRL and MTN to translate what is conventionally a single task problem into what is into a multitask one?
Yes, that's a very good point. So let's think about it first from sort of philosophical perspective, what it means for a single task problem to be multitask, and then we'll talk about the engineering side of it. So let's go back to that self-driving example. So you have this algorithm which can drive your car, and it's trained and tested and evaluated on concrete roads. And today there is rain, right? One view is that you can say these are basically the same tasks. It's just a generalization problem, and multitask learning is not needed. And sure, that's a valid perspective. Or you could say that multitask learning is not just a problem; it's also a solution. So the problem is I have to train a car. I have to train this algorithm that can drive car on different surfaces, and I'm going to think of each surface as a different task. And so in this case, the multitask learning becomes more of a solution and less of a, like it's not the problem that you started with, but now you are hoping that work in multitask learning would be able to solve this other problem. So from that perspective, yes. And you can start with a single task problem and you can convert it into a multitask problem. A lot of real life problems are actually like that. So even if we forget about driving and all these things, you train your model on one data set and that's it. I mean, sure, so you have trained it on one data set, and then you deploy it in real life. And when users are interacting with it, when people are interacting with it, you are gathering more data, and there's no necessity that the new data or the new sort of interactions that people are having with this model would be similar to the kind of interactions or data that you had initially collected. So the data distribution could change, and it's more likely to change than not. And then the question is, so you had this one data set D1, and then you have this new data set D2, and they are probably not very similar. So are you going to solve this as a multitask learning problem? Yes, you can, or you could say that no, these are just the same thing. I'm just gonna merge the two data sets into one big data set, and it's still going to be a single task problem. So you can model the problem different ways, but once you start thinking about multitask learning as a solution space as well, and not just a problem statement in itself, it opens up a lot new possibilities. So that's like the the intuition side of it. From an engineering perspective, yes. As I was mentioning, different wrappers in the MTIN library. There's a wrapper where you can take a single task environment and just make a multitask version out of it. In the simplest terms, it means that the wrapper changes your interface so that it becomes compatible with the MTRL algorithms. But since you also have control over this task state, you can change the task state, and then you have a multitask version out of it. The question would be, how do you change the task state? And that's going to depend on what you are trying to do. So the exact change that you make would depend on the downstream use case, but can you do it in terms of engineering or implementation? Yes.
Oh, that was really interesting. I did not realize that the model retraining or online training perhaps would actually be candidates for a multitask learning paradigm.
Yes, I mean, the moment you start thinking of it as a solution, a lot of possibilities come up.
That's very interesting. Are there do you have any challenges or nuances that you would like people to be aware of when they're translating what is conventionally a single task into a multitask problem?
Yeah, I think the sort of the thing to be careful of is, do not transform one problem, do not transform a problem from X to Y because you want to solve Y. I mean, if you want to solve Y, then that's great. Like there are plenty of problems in Y to solve, right? So if I start with a single task problem and I force it to become a multitask problem by changing the problem definition and so on, and then I solve it, yes, that can be solved. But so the point is, there should be a separation between what needs to be solved and what I want to solve. And this is, I think, very important for us as a community, because a lot of times we start with a problem and we unnecessarily twist it into a problem for which we have the solution. It's good to satisfy the intellectual curiosity and so on, but when you're thinking about the real life use cases, it's much better to focus on the original problem statement and think about what's the best way to solve it. And if the best way to solve it is to transform it and make it a multitask problem, that's great. Like there's nothing bad. But don't think of multitask learning as a hammer, and then you have to apply that hammer on all the problems you see. So that would be one sort of big pitfall, I would say, where people see a new approach and they're like, oh, everything can be solved using this. Yes. Is it the most optimal way? Probably not. Yeah.
I think we may have opened up a Pandora's box over here. Nitish wonders if a multi-agent RL can be approached as a multitask RL.
So you can, but so you have to think about it from the perspective of what do you control, or what do you have control over, which means that okay, let's think of a nuanced example where we can break it. So if you can control the if you can control all the different, okay, you have an environment where you have multiple agents and you can control all the agents, which means you can control what actions all the agents are taking, then probably it makes more sense to model it as a multi-agent problem. Uh, if you are more in a setup where you don't have any control or you probably can't even observe the other agents, then probably you could think of it as multitask. Probably not. Yeah, I think I probably need more context on the specific thing, but probably multi-agent would not seamlessly transfer into a multitask RL problem.
Thank you, Nitish. If you are able to provide more context for Shagun to be able to answer this, feel free to drop it in the chat. Shagun, I wanted to ask you, are these libraries being used at Facebook? I know they have been developed at Facebook Research, so it's very likely they are.
Yes,
What,
yes. I think at this point we have used them in about 4 or 5 different papers. I've lost track, but yeah, they are being used internally. People I mentioned in the initial slide, they are contributing new environments. Olivia recently contributed this multitask, the move fast RL, the network congestion control environment, and we are using these libraries internally for our own research use cases.
stepping back a bit from multitask RL, not yet asks a question. How does reinforcement learning compare to deep reinforcement learning, I guess? What's the difference?
Okay. If you think about it as a problem setup, sorry, if you think about it as a solution setup, reinforcement learning is the broad family of solutions that you have, and deep reinforcement learning is sort of one specific instance of it. In practical terms, what happens is let's take a concrete problem. So I want to make a self-driving car, and then I model it as an RL problem. And when I model it as an RL problem, I have the state, action, and reward, and everything, and I know how to solve this problem. But in practice, I cannot solve it because the state is going to be extremely large. So what would be the state for self-driving car? Probably the state is the pixel observation that I see in front of me, and that's very high dimensional. So even though I have a recipe to solve it, that recipe is not it would not be able to solve it because my state is too large. So the reinforcement learning solution exists, but it's not sort of doable with the vanilla reinforcement learning. So then you say, oh, but you don't need the entire pixel observation. You can encode it into a smaller, fixed dimensional representation, and for that you use a deep network. And then you say, oh, my policies need not be shallow; they can be deep networks, and so on. So you have the recipe. You swap out the pieces, or you implement the different pieces as deep neural networks, and that becomes deep reinforcement learning. But most of the recipe is still coming from reinforcement learning. It's just that you're materializing that using neural networks, and then it becomes more of deep reinforcement learning.
Thank you. That was quite crisp. Shifting gears a bit, I was wondering, what are you most excited about the future of reinforcement learning?
So the aspect that I'm more sort of excited about is this idea of lifelong reinforcement learning. So when we said multitask, right? I said you have read one book. I said that you want to read 2 books, and there's this knowledge that you can share. But humans are not doing this just at the level of task or so. We are doing it throughout our life. And an example of that is we learn how to walk, and then we learn how to run. And if I ask you to climb a mountain, the fact that you know how to walk and you know how to run, those skills become useful for you. But when you were learning how to walk, you probably did not imagine yourself climbing a mountain, or you were not preparing for that. So in multitask learning, we generally sort of have this high-level assumption that we know the task that we care about. But in life, that's not how things happen. So probably a skill that I've acquired today would be useful 20 years from now, and I don't even realize it. Or maybe tomorrow I'll need a skill that I've never ever acquired, but now I need to acquire it. So there's this idea that humans are lifelong learners. We are learning throughout our life, and we are able to transfer skills and so on across a much wider time horizon, across ages, across decades. How do our reinforcement learning agents, or in general, how do our machine learning agents do that? So that's the broad lifelong reinforcement learning problem. So that's the problem I'm very excited about. Yeah, I don't know how. I mean, there are different manifestations of how it could look like. I don't know which manifestation is the most optimal one, or the one that's most likely to work.
Super trivial problem you have chosen, Shagun.
Yeah. Choose a problem that we know that humans can solve, and hopefully, since we can solve it, we'll be able to train our algorithms to solve as well.
I like that philosophy. Um, just moving back a bit, like what are you most excited about in the PyTorch library that I believe you have used to develop these?
I mean, the question is, what am I most excited about, the MTRL and MTM libraries?
Yes, that could be the question as well. And after that, I'd also like to know what are you excited about in PyTorch?
Yes, yes. Okay. So what am I excited about in the library? So um, I think I'm very excited and very happy that there are these, the building blocks are still very composable, and that empowers a lot of research that we do. A lot of algorithms can be broken down into these components, and that's not how they look if you look at an isolated paper. So if you look at an isolated paper and you think about how to implement it, that will look very different from what you get with the library. But so it's like, you make a big investment at the start, and if you make that investment right, you would be able to make a lot of other problems easier. So the part which I'm very excited about is this, you have these building blocks and you can add new algorithms sort of trivially because you don't really need to implement the full algorithm. There's probably a piece missing and you just implement that piece. So for example, I mentioned we want to have hyper networks. If we implement hyper networks as a block, then all other algorithms would already support it. So it's not like I have to implement n algorithms. I have to implement one algorithm correctly, and then people can start composing it with whatever they like. So that's the part I'm very excited about in the libraries. PyTorch, there are many things, and there are many things that I like PyTorch for, and there are many things that I'm very excited about PyTorch for. So I'll probably start with the things that I like about PyTorch. The first thing is the community that you guys have. It's I spend a lot of my time in this discourse for PyTorch users, and now there's a new discourse for the PyTorch developers. And I'm not a PyTorch developer, but the amount of the new things that I learned just by reading at the comments and how the developers are thinking about it, that openness, that is super useful. I also spend a lot of time on the Slack. I probably have never posted anything, maybe one or two messages, but just being there, just looking at what community is talking about, that gives me a lot of context which I otherwise would not have. So this openness, that is super useful. The ecosystem that you guys have developed, that is also very useful. I mean, if I want to do X, I know there's sort of a reasonable place to look for that library for doing X, and if I'm not able to find it, then I can go to GitHub and search more. But having this sort of source of truth is very useful. Third thing I like about PyTorch is I can choose the level of complexity. So I could say, look, this is a research project. I don't have time for scale, or I don't care about scale. I just need to get this thing done, and I can do that. Or I can say, look, everything is good, but this specific piece is what is slow, and how do I speed it up? Oh, there's JIT. Oh, there's short script. Okay, I know how to speed it up, and I don't have to speed up the entire code base. I can just speed up the part that I care about. So I can embrace complexity. I can embrace this sort of more powerful constructs as and how I need it. It's not like you take everything or you leave everything. So there's a sweet spot where I can say, look, I don't care about other things. This is what I care about. Give me that, and I use it. So this feasibility where you can decide how complex or how advanced features you want to use, depending on how what your use case is. That is very powering. What am I excited about in PyTorch? I'm spending a lot of time reading upon RPC and how RPC works on PyTorch, and I think that's super awesome. That is one thing that I'm very, very excited about. Why is it relevant for my work is, so I think till 1.8, RPC did not support transferring CUDA tensors, and that's sort of a limitation, but with 1.9, they already have the beta support, which is awesome. And going forward, the support would become even better. And this is very useful for distributional reinforcement learning when you have a lot of actors collecting data from a lot of environments and training a single policy. So this becomes very useful there. Some of the other things which are coming up, functional transformations, and I think these are also very useful. There's this sort of I'm not a core developer or anything, or it's not likely that I would be using things like FX very soon or anything, but just knowing about it and knowing about what are the possibilities, it empowers you. You know that you this is what you're designing. If tomorrow you need to scale it up, this is the extent to which you can scale it, and you don't have to commit to scaling it right away. So there's this gap, and if this gap becomes a problem, PyTorch has a solution for it, and it would fill the gap. So yeah, these are some of the things that I'm very excited about for PyTorch, and the reason I use PyTorch a lot.
Thanks, Shagun. That was so comprehensive. For everyone who's been listening, I I totally agree with Shagun. That's my favorite part about PyTorch, the community that's so vibrant and diverse. And even on the forums, the two forums that he mentioned,
Yes.
that it's very unlikely that you won't find what you're looking for on the forums. And if that does happen, just posting it out there immediately attracts so many different perspectives and viewpoints. It's not even funny.
I
And
can give a personal example, and this happened about 2 or 3 or maybe 4 years back. So early days of PyTorch, maybe 2017 or 18. So a new build had come out, and the build had some problem or something. And I don't even know if we had Slack or something. There was some communication channel, and I just posted on it and said, "Look, I'm trying to install it. It's not working." And I think within 5 minutes, a core developer DM'd me and said, "Oh, we are sorry for it. We have fixed it. Can you just try downloading it once again?" I was like, "Oh wow, okay." So they are very responsive. It's not like they do the release and then they are gone or something. So those were the very early days, and the kind of engagement I saw from the community, that a random user comes in, they say, "Hey, the build is not. I'm not able to install the latest release or something," and someone jumps on it and fixes it right away. That's amazing. So yeah, I really cherish that part of the community.
true. I mean, the project has grown so much, but there is still that element where developers actually interact with the
Yes.
users in an almost intimate setting. In fact, I want to take this opportunity to plug in Edward Yang's podcast. He's one of the core original developers on PyTorch, and he has a podcast out on Spotify and honestly wherever you get podcasts about the internals of PyTorch. And these are like really bite-sized sort of episodes where you get a very high-level understanding of what's actually going on under the hood in PyTorch. So definitely check that out if you're interested. I'll add a link to that in the video description so that you can easily get to it.
And let me vouch for that, because again, I'm not a PyTorch developer. I don't usually care about the internal details. I have been subscribed. I've been hearing his podcast, and it is useful if you don't have to be a PyTorch core developer to be able to enjoy that or benefit from that. It's useful even if you are a casual PyTorch user and you have just more curiosity about how things work internally. So that's super interesting and super useful for that.
Yes. Um, I see Nitish has provided the context for his question, but
Okay.
unfortunately we are at time. So Nitish, what I will do is I'll work with Shagun to get a response to this, and we'll add it to the YouTube comments. Stay tuned for that. I'll ping you when we do have this. Um, this was really awesome, Shagun. Thank you so much for this discussion and for joining us today and taking time out of your very busy schedule.
No, thank you very much, and thank you for investing in your community. Right, the community voices is really the community, the people who are developing it. So thank you for investing time into it. It's great to be part of this community.
It is that. Yes, I totally agree. Um, Folks, follow Shagun on Twitter if you want to learn more about what he's up to, what he's working on. You see his handle on the screen next to his name. You can also star the projects on GitHub to just be aware of what else is happening and just keep up with that. Also, if you enjoyed this episode, please like and subscribe to our channel so that you can be notified of all new episodes that are coming up. On behalf of everyone at PyTorch, thank you for being part of our community and joining us today. If you have any suggestions on guests or who you'd like to see on the show or anything that we should be doing to make this better, please feel free to let us know. You can DM me on Twitter. That's my handle next to my name. Until next time, torch on.
Thank you.
Thanks. All right.
Bye
See you soon,
bye.
Trevor.